This is the graph of x squared minus 6x plus 25 for real numbers x. Now the graph doesn't cross the horizontal axis, and as you found earlier in the chapter, that means that the corresponding complex polynomial, z squared minus 6z plus 25, has no real roots. On the other hand, you did find that it has two complex roots. They're shown on this Argand diagram as the complex conjugate pair 3 plus 4i and 3 minus 4i. What do you notice about the graph and the values of the two complex roots? Well, the minimum of the graph is at x equals 3, and x equals 3 is also the real part of the two roots. Now, what will happen to the roots if we change the value of the constant, 25? In other words, if we look at the family of graphs, x squared minus 6x plus c, and the corresponding complex functions where c is real. Now I'd like you to look at the same sequence again, but this time we'll show you the roots marked off on the Argand diagram. What's happening to the roots? Well, the roots start off as complex ones and eventually end up as two real ones. As the graph gets nearer and nearer to the horizontal axis, the two roots get closer until at this point the graph touches the horizontal axis and there's one repeated real root. So this polynomial, where c equals 9, has a repeated real root at z equals 3. From here, the graph cuts the horizontal axis in two places. So the roots are real, and they are positioned at equal distances on opposite sides of the value 3. That's shown in the complex plane on the Argand diagram by the way that the roots spread apart horizontally along the real axis at the same rate. So quadratic polynomials always have two roots, either as a pair of complex roots, as a single repeated root, or as a pair of real roots. So what happens with cubic polynomials? This is the graph of x cubed plus x squared minus 17x plus 175. What does this picture tell us about the roots of the corresponding complex polynomial? In particular, how many roots does this function have? Well, as it's a cubic polynomial, it must have 3 roots. But what are they? The graph shows that there's only one real root, where x equals negative 7. So the other 2 roots must be complex. In fact, they must be complex conjugates. If we factorize, you'll recognize an expression you've already solved in this chapter. Indeed, the quadratic part is the one we looked at earlier, as you can see in the Argand diagram. But what happens to the roots if we change the value of the constant term and look at the graph of x cubed plus x squared minus 17x plus c, where c is real, and at the roots of this complex function? As the value of the constant decreases, the two complex roots get closer together, until here, the graph just touches the horizontal axis, and on the Argand diagram, the two complex roots would coincide to give a repeated real root. But here, the graph crosses the axis in 3 places, and the Argand diagram shows 3 real roots spread out along the real axis. So what will happen to the roots if the curve is moved even further down? 2 of the real roots get closer and closer together until they coincide as a repeated real root. Lowering the graph further, we find ourselves back with only 1 real root, but, as the Argand diagram shows, a pair of complex conjugate roots diverging from the real axis. So cubic polynomials have either one real root with a pair of complex conjugate roots or three real ones. So what happens with a quartic polynomial? This is the graph of x to the fourth minus x cubed minus x squared plus x plus 1. How many roots does the corresponding complex function have? And what would they look like on an Argand diagram? Well, the graph doesn't cross the horizontal axis anywhere, so you might imagine that all four roots are complex. And indeed they are. If we look at the Argand diagram, we can see that there are two pairs, each pair situated symmetrically on either side of the real axis. So what will happen to the roots if the constant is changed? The pairs of complex roots move together until here, where the graph just touches the real axis, the roots on the left coincide to give a repeated real root. Now, as the graph is lowered still further, you can see in the Argand diagram that these roots move apart, while the remaining pair of complex roots moves closer together, until they too coincide to give three real roots, one of them repeated. Lower still, and on the diagram, both pairs of real roots diverge as the graph crosses the x-axis in four places, until the two middle roots meet when the graph touches the x-axis, and then separate as a pair of complex roots. The graph now only cuts the x-axis in 2 points. So quartic polynomials always have four roots, either as two pairs of complex conjugate roots, two real and two complex, or as four real roots.